Yeah. So we have the this is the periodic functions function type, and I can tell you any periodic function can be decomposed into, listen this carefully, okay, in good concept. Any periodic force function, any periodic function can always be expressed in terms of summations of harmonic function of the various frequencies. So which means any periodic force functions can be expressed in terms of the constant plus sine or cosine omega t, sine or cosine omega 2t, omega 3t, etc., etc. And what is the number of omega 2t, omega 2, omega 3, etc., that one can be determined based upon the given type. So the whole concept is this. As long as we are given the periodic functions, you should expect you must, at the very first step, decompose this function in a certain way into the combination of the constant sine or cosine, whatever. And once you have this form ready, then you simply, again, repeat it, your calculation, taking this template and to response to individual terms. Are we okay? Okay, so now the issue is this. You can ask me, how do I decompose such a periodic function into this form? Then that is a Fourier series expansions. So what you have learned before about Fourier series expansion, Fourier series, that is where we apply in engineering to here. And that is to help us at least to express any periodic function into the combination of harmonic terms. That's it. So maybe that one, when you learned in Fourier series, that maybe this kind of concept has not been reinforced, but here I give you this concept. Okay, so bear this concept in mind, then no matter how apply the techniques to get this one from here to here, then that's a different story. We can try to polish the skills over time. Okay, so given this one, here I already do the expression. We are given this pulse function. The pulse function have a period of time t. Okay, basically this is we call the 50% duty cycle PWM pulse module PWM pulse with modulations. Good, thank you. Okay, so basically this is a one period, second period, third period, and this one taking the pulse is on for only half of amount of the period, so we call it 50%. And actually you can have any number, say 10% or 60%, whatever. Okay, so that is the one here. So for given this one, we can apply the Fourier series expansion, and this is the result. I simply skip off all the details. This is the final result. So basically for these questions, it's very straightforward. Let me revise this one. Sorry. So basically the similar problems, and then let me copy this one here. F0 divided by 2 plus 2F0 divided by pi sine omega t plus 2F0 divided by 3 pi sine 3 omega t. Okay, so basically the problem is like this. I copy that from there to here. Okay. So in this way we can just modify. Maybe I can rewrite again. You can write with me. Okay. So basically right now we have three terms. Okay, and how to do it? For the first term, this is a constant. And how do we apply this constant using this template? And I can share with you for this template, for this one, you can imagine this one can be rewrite into F naught divided by 2 times, for example, say cosine 0 times t. Okay? So if you would treat that frequency as 0, then you can use the templates there. So for this case, again, the magnitude equal to F naught. The magnitude of the force is F naught divided by 2, and then divided by spring constant. And here is 1 minus R squared. Let me copy the template first, and then plug in the number of seconds. So for this case, I would say R equal to the ratio of the working frequencies between to the natural frequency. The working frequency equal to 0. Okay, so under this case, you can do the calculation, and then here is in sine, here is in cosine. So basically, it's cosine, and then say 0 t minus phi, and here if you like to calculate the phi, will be equal to arctangent, and let me say this is R1, 2 zeta R1 minus R1 squared. Okay, you simply plug in here. Okay, repeat the same thing, and then now for the second terms here, then we can have the similar form. So that is the magnitude equal to 2 0 and divided by pi. This is the magnitude of the force term, and divided by spring constant. Again, we copy from the template. And the same thing here is 1 minus R squared plus 2 zeta R squared. And for this case, R will be, say, R equal to R2 equal to that frequency is omega, and divided by omega n. Okay, and then the term is times, this is sine, and omega t minus phi, and let me call this is phi 2, okay? So phi 2 equal to arctangent, 2 zeta R2, 1 minus R2 squared. Okay? And then plus the final one, the response to these terms. So that term, again, plus. So the magnitude is 2F now divided by 3 pi and divided by spring constant. So basically the same thing. And so R will be equal to, the working frequency is 3 omega divided by omega n. Plug in here, and that one basically is sine 3 omega t minus phi 3. So phi 3 will be equal to arctangent, and 3 2 zeta R3 1 minus R3 squared. So this is R3. So that's the result for this problem. So you see again that is repeating our previous calculations. So here, luckily, we only have 3 terms, but I can tell you, or even you know that usually when we do the Fourier series expansion, how many terms there? Infinite. The number is infinite. Oops, sorry. That isn't supposed to be. So that means, in theory, your calculation rigors will be huge this time for the coming up homework. Not my fault. That's the system like should be like this. Okay? Feel good? I don't think so. I don't think so. I'm not threatening you, but you're going to have a lot of writings unless you do the program and the program benchmark good. Then, yeah. Sometimes I'm asking emails to some of you, hey, give me the copy of your scratch work, because periodically I look at your submission history. Say if you make 100 attempts, from my computer I can see you make 100 attempts at which day, which time. Okay, I know exactly. And if you only make one single attempt and then make 100 points, I don't believe it. So I would, in that moment, I will asking. So quite a few incidents you receive my emails ask about this one. So just let you know. I think I mentioned this one at the beginning of our class. But